Okay, I think we should start. So I guess most of you have left for Thanksgiving. Okay, only 1, 2, 3, 4. Only first students. Okay. We're gonna start some new topic, but most people have some. Anyway, so let's start. So in a previous topic, we discussed about the clustering, a very important problem in unsupervised learning. So clustering is to automatically group the data points into different cluster structures, right? So the most important algorithms to perform clustering is called k-means. So k-means is kind of cluster-centered algorithms, right? The most important thing for k-means is to find out the centers of clusters. And given the centers of clusters, we just compute distance between each data point and the cluster centers and assign the clusters, assign the points to the cluster who has the closest center. This is the k-means. This is the idea of k-means. So the k-means basically repeatedly update the cluster memberships and cluster centers. Have a seat. I moved. Not more student. So basically, in one iteration of k-means, we first fix the cluster centers and update cluster memberships. And then you fix the cluster membership and update the cluster centers. So both steps are very easy to compute. And then you continuously, alternatively update cluster memberships and cluster centers until convergence. And in theory, we can show that this alternative updating is to minimize a SSE. The SSE, if you still have an impression, is SSE is a summation of the square distance between every data point and its cluster center. And it turns out the minimization of SSE corresponding to this alternative updating procedure. And then we discussed a few, based on this SSE form, we discussed a few commonly used variants of k-means. For example, if I redefine the distance, I do not put a square of the distance, square of Euclidean distance in the SSE. Instead, I wipe off the exponent 2. I just calculate the summation of the distance, the square norm, not the norm, not the square of norm. Then the k-means becomes a k-median. Right? Of course, you can define other types of distance metrics. For example, k-method is defined based on another metric. And in the lecture given by Claire so this Monday, I should wrap up the further extensions of k-means. If we use a probabilistic framework to reinterpret k-means, it becomes cluster mixture models. And then you directly represent the memberships by some multinomial random variables. And the most commonly used way to learn cluster mixture models is called EM, expectation maximization algorithms. You will learn them in your advanced machine learning data science class. And also, someone we may wonder how can we automatically determine the number of clusters. So for k-means, there's no other ways. We actually introduced several tricks to determine, to try different number of clusters, pick up the best one. Right? But there are some algorithms which can automatically determine the number of clusters as well, like mean shift. So in the future, you also learn mean shift algorithm as well. So that's all about the subject of clustering. So, and then we will begin with the last topic in this class. It's called classification. So what is classification? We spent quite a few lectures talking about regression. So the setting of regression is as follows. So suppose you are given like D explanatory variables or features. We want to use these D features or D variables to predict the value for target variable Y. So when we discussed the regression setting, we emphasize that this Y must be continuous or real value. But now if we change Y to be discrete, then it becomes classification. And in our class, for simplification, we mainly focus on binary classification. That means Y is either a positive one or negative one. And in some cases, in some literature for binary classification, they will just assign Y to be 0 or 1, but it doesn't matter. It's just the notations difference. So those D explanatory variables, in a classification context, we call them features. And those D explanatory variables, or those key feature values, can be considered as a representation for some instance or object. For example, if I want to classify myself to be like handsome or not handsome, right? I can extract like many features to represent myself. For example, my weight, my height, my age, gender, etc. So that's the numerical representation for an instance. So which are represented by a D-dimensional feature vector. And then we want to map this feature vector to a binary label, either 1 or -1. That's the definition of the classification problem. And examples, there are too many examples for classification tasks. For example, I want to predict whether tomorrow the temperature of tomorrow goes up or goes down. I want to predict I will be able to find a good job after I graduate or not. Those are all classification problems. And to finish this classification problem, the first step is to find out or extract a set of features. And then based on those features and labels, want to construct a model. So how can we construct this model? This is the next question we need to address. An idea? If I want to map the feature vector to some binary label, how should I do that?
We cluster all of the data into two groups, and then
Yeah, that's one way. Of course, that's one way. But do you have another idea? Because right now we have some label information for those instances. Actually, in most cases, we won't necessarily use the unsupervised learning techniques. Right? So we can think of some general approach. Right? So consider what we have learned in the regression problem. To predict, suppose now Y is continuous values. To predict Y in terms of those D explanatory variables, what should we first propose?
linear regression.
Yeah, a regression function. So in a regression model, we need to come out with a function. For linear regression, this function is simply a linear combination of those D features, right? So simply is alpha 0 plus alpha 1 x1 continuum and alpha d xd. And we use the value of this regression function as our prediction. right? This is a linear regression. Of course, if we replace this linear function by polynomial, we actually use the polynomial regression model. And the training would be minimize the SSE. The SSE is simply the summation over all the training instances. And each segment is just a square of the area that is using the regression function to predict the true label, the true value of the target variable and take square. So minimize this SSE to estimate alpha 0, alpha 1 to alpha d. So similarly, for classification, we need also to come up with a classification function. So we can also write down this function as denote this function by L. And then the problem is that how can we classify x into a positive 1 or minus 1 according to the function value of L? How can we do that?
It's positive or negative.
Yeah, very intuitive, right? So I can simply, suppose I have some classification function here, right? And now if I want to do prediction, I just check the function value. If it is, say, a negative, then I assign the label of x to be 1. Right? Otherwise, if the function value is negative, I assign the label to be a minus 1. This is called a classification rule. It's a bit different from the regression case in that the regression function value directly determines our prediction, right? Because regression needs to estimate the continuous values. But for classification, we need some extra rule. We need to determine whether the function value satisfies some condition, satisfies some rule. If it satisfies this rule, meaning that the function value is negative, we will assign a positive 1 as the label. Otherwise, we'll assign negative 1 as the label. So this is the idea. So we'll start with the easiest but most widely used classification model called linear classification. So linear classification is very similar to the linear regression in that the function form, the classification function, is also a linear function. So the traditional notation here, we won't use alpha 0, alpha 1 to alpha d to denote the classification weights. Instead, I use a b to represent the intercept. And then for each feature, x1, x2 to xd, I introduce a weight. So the classification function becomes b plus w1, x1, plus w2, x2, continue, wd, xd. So this is a linear classification function. Then, to classify any feature vector, we just evaluate the corresponding classification function and test whether the classification function value is bigger than 0 or not. If bigger than 0 or no less than 0, we just assign it's a positive sample, otherwise it is a negative sample. And a commonly used trick, which is similar to the linear regression model, we can write the classification function as inner product. How can we write it?
And with the w vector and your x vector.
Yeah, of course. And also we want to augment the feature vector by 1, right? So that we just leave 1 in a product rather than some extra term. So we can augment our x, say, denoted by x hat, by inserting 1, a constant 1, into the features. So it's 1, x1, x2, continue, xd. This is our augmented feature vector, and also our augmented big vector is first the intercept B, and then the first weight W1, second weight W2 until WD. And then our linear classification function can be represented by the inner product between the augmented feature vector. That's another common used notation in the linear classification. But today we still focus on this canonical form. We still focus on this form. So this form can be written as B plus an intercept plus the inner product between W and X. So here I directly write it as W transpose X. So to emphasize they are both vectors, so I put an arrow on top of them. So now let us look at several important geometric properties about linear classification. So here Lx is simply an intercept plus the inner product between the width vector and the feature vector. We'll look into this linear classification function by looking at the equation such that the function equals to 0. You can imagine it's kind of at the boundary, right? At the boundary. So if the classification function is bigger than 0, it must be classified as positive examples. Otherwise, it is less than 0, must be classified as negative examples. But what if I want to look at all the instances such that the classification function value is exactly 0? What kind of geometric properties does it represent? We can start with a simple case, right? So for linear classification, it becomes B times the inner product between W and X is 0. So this equation actually defines some plane. So if X is two-dimensional, X is two-dimensional, then W is two-dimensional, and then this equation becomes like W1 x1 plus W2 x2 equals to 0. What is this in a two-dimensional space? It's just a line, right? Just a line. And of course, this line segment or partition the whole two-dimensional space into two parts, right? On one part, say here, all the data points on this part are positive examples, right? Because the function value is bigger than 0. All the other points on the other side will be a negative example. So if we're now staying in a three-dimensional space, then it becomes a plane. If X belongs to a three-dimensional space. From our stereometry knowledge, this equation determines a plane. So you can imagine there is a plane which is B plus W transpose X equal to 0. And of course, this plane also partitions the whole three-dimensional space into two parts, right? In one part, all the points are classified into positive examples because their classification function is positive. And in the remaining part, all the points are classified as negative examples. So we can easily generate our observation into a d-dimensional space. In the d-dimensional space, this equation, that is the classification function B0, determines a hyperplane. because it's a high-dimensional space. So we cannot say it is a plane. A plane is only meaningful for two-dimensional space. So for the high-dimensional space, we call it hyperplane. But for visualization, you can still imagine it's a plane. So we now know that in this high-dimensional space, so X three-dimensional space, the classification function being 0, meaning the classification boundary determines a hyperplane. So write it down here. Equals to 0. Again, this hyperplane separates the d-dimensional space into two parts. On one part, say the point here, their classification function value is positive, so they are all classified as positive. And on the other side, it becomes negative examples. So we call a subpart, which is produced by using this hyperplane. We use the separative subpart is called half space. Of course, you can call the other side, the part on the other side, as half space as well. That's just a definition. So this is one geometric view of the classifier. And next important property is about the direction of weak vector. So what is the direction of weak vector? Given the classification hyperplane, do you know where is the direction of the weak vector?
It's normal to the.
What?
It's normal.
It's normal. Normal, what do you mean by normal?
It's perpendicular.
Perpendicular. Any other idea? Yeah, that's right. Very good, that's right. So the v vector, W is always perpendicular or orthogonal to the classification hyperplane. So to verify this, you can check. You can check, how can we check that? We just check whether W is orthogonal to an arbitrary line, proportional, or not proportional, parallel to this hyperplane. How can we do that? We can randomly pick up our 2-point state on this hyperplane, say x1 and x2. So suppose this is the origin. This is the origin. So we know here is x1, and here is x2. Right, x2, right? Then to get a line which is parallel to this hyperplane, we can just subtract x1 by x2, because if you do the vector subtraction, you end up with this line, right? Because this line must be parallel to the hyperplane. And then I just check whether W is orthogonal to this line, because x1 and x2 are chosen arbitrarily. So if we can prove that W is orthogonal to x1 minus x2, then this shows that W is orthogonal to an arbitrary line parallel to this hyperplane, right? Then how can we verify W is orthogonal to this?
Cross product of W x1 minus x2 should be 0.
Yes, we can simply check the inner product, right? Inner product between W and this. And now we need to use the knowledge here. Any points which stay on this line have W transpose X plus B equals to 0, right? That means for x1, we'll have W transpose x1 equals minus B, because this equation holds, right, for x1. And similarly for x2, we have W transpose x2 equals to minus B. So we can say actually, if we multiply into this parenthesis it immediately becomes 0, right? Because the two terms are exactly the same. So now we verify that W is orthogonal or perpendicular to the classification hyperplane. This is a very important conclusion, because you need to use this geometric interpretation to understand the support vector machines in your future courses. So this is the first property. W is proportional, or is orthogonal to the hyperplane. The second property is regarding the intercept B. The first property actually characterizes the properties for W, right? So naturally, we want to look into the properties of B. So what kind of properties does B have? So here I first give you the conclusion. So we can show that B equals to the distance between the origin 0 and the hyperplane, classification hyperplane, is the absolute value of B divided by the norm of the weight vector W. So later we'll discuss how we choose W. But you can imagine if our weight vector W is unit vector, is normalized, then the distance between the origin and hyperplane is simply the intercept B. Right? But how can we come out with this conclusion? This is not very straightforward. So you need to use one conclusion. That is the formula to compute the distance between an arbitrary point and this hyperplane. So let me denote this arbitrary point by Z. So the distance between Z and this hyperplane, let me denote it by H, is computed as follows. So in the denominator, you just evaluate the classification function in terms of Z and take the absolute value. So here it will be the inner product between W and Z plus B, and then divided by the norm of W. So this is a general formula. This is a general formula. So you can imagine if Z stays on the hyperplane, and then because classification function value will be 0, right? So distance 0. So it's natural, right? It's one immediate verification of this formula. Right? But for an arbitrary Z, its distance to this hyperplane can be computed from this formula. But how can we come out with this formula? How can we come out with this formula? We can use some vector operations and stereometry knowledge. So now let us imagine I just want to compute the distance, right? So what should I do? I just draw a line which is orthogonal to this hyperplane, right? And also pass D. And then there must be a cross, that's intersection between the line and this hyperplane. Right? So I denote it by Z hat. And then how can you represent the difference between Z and Z hat? How can we denote it? How can we represent this difference? We know from the vector additions, this corresponds to a vector, right? So starting from Z hat pointing to Z. So if you can imagine the distance is D. So if you assume the distance between Z and this hyperplane is D, right? So this vector actually can be represented by the distance times a direction vector. Remember, a vector consists of two pieces of information. One is the length, the other is the direction, right? So now we know the length of this z minus z hat is the distance, right? Then we represent this vector. We only need one direction vector, so we can denote this direction vector by u. So the problem is, how can we identify this direction vector?
It's the same as W.
Yeah, exactly, right? Because as we just discussed, the direction of W is always orthogonal to the hyperplane. So we can normalize W and use normalized W as direction vector. But here you should be careful that if Z is on the same side with W, I mean the angle between Z and W is less than 90 degrees, then you can directly use normalized W as your direction vector. Right? Otherwise, if Z is on the other side, so if Z is here, then the direction is completely opposite to W. That's why in our final formula, it becomes an absolute value rather than some value without absolute. So let us just consider the case that the direction of this difference is the same as the direction of W. So we can represent Z minus Z hat by the distance multiplying the normalized W. Okay. And further, we can look into the left-hand side. So we can multiply both hand sides by both sides by W again. That's the inner product. That's the inner product. Right? So if we do the inner product with W for both sides, so we have a W transpose on the left-hand side, which is Z minus Z hat. The right-hand side is D times W transpose and W over norm of W. And let us look at what do we have, right? So first, on the right-hand side, in the denominator, it is W transpose W, right? So that means it is norm. It is square norm of W. Then you divide by W. One norm of W is cancelled. So on the right-hand side, it becomes norm of W. Right. So what about the left-hand side? We need again to use this condition. Remember, Z hat stay on the hyperplane because it is an intersection between this line and this hyperplane. Okay. So we can multiply W into this parenthesis, so get a subtraction between two terms. And then we can plus a intercept and then minus an intercept. So it is zero. It is zero, right? It doesn't affect the left-hand side. And now we merge them together. We have a first term will be W transpose Z plus B, right? Because we merge them together. And then we merge the remaining together minus the W transpose Z hat plus B. This is the left-hand side. So what can we observe from this left-hand side?
The last term is 0.
Yeah, this term is 0, right? Because Z hat stay right on the hyperplane, right? So the classification function value must be 0. So this part is simply 0. This is 0. So now the left-hand side becomes the classification function value is evaluated as Z. Okay? And the right-hand side becomes the distance times distance multiplying with the norm of the vector. Then we'll get here. Distance is simply the classification function value divided by the norm of the weight vector. Be careful because here we assume the direction of Z minus Z hat is the same as the direction of W. So we don't put an absolute value here. If you also consider the other case where the difference between Z and Z hat along this direction, which is opposite to W, then here you should put a minus sign here for the unit vector. And then you end up with a minus sign here. So if you unify two expressions together, you have to put an absolute value on the classification function value. And this is reasonable because the distance must always be non-negative. Right? So you must ensure that both the denominator and numerators are positive or non-negative. So given this formula, we can consider the distance between the origin and the hyperplane, right? How can we do that? We just replace Z by 0, right? If we replace Z by 0, we immediately obtain this. Any question at this point? Okay, good. So the one important property of classification is that the same classifier may not necessarily bind to one same set of WB. This is very different from linear regression. Right? So imagine our given our classification function, which is W transpose X plus B. Right? So what if I multiply W and B by both W and B by some scalar, like by 10? What will happen for our linear classifier? So if I multiply W by 10, I use like 10W and 10B to construct a new classifier. What's the difference between this new classifier and the old classifier?
Just scratch it.
Think more. To answer this question, we need to remember the classification rule. Right? So remember, if you want to do the classification, we just check whether the function value is bigger than or equal to 0 or not. Right? So if it is bigger than 0, then the classifier is the classification is positive. Otherwise, its classification is negative. Right? So now, if we multiply W and B by both some positive constant, what will happen? What will happen to the classification results? Does the classification result change? No, nothing happened. For the original WB, say the classification function value like 5, right? So now if you multiply WB by 10, then the classification function value becomes 50. Right? But both numbers are positive, right? So classification results are the same. And similarly, if the classification function value is negative, right? You multiply a negative value by some positive constant, it's still negative. It doesn't change the classification results. So this is the difference between a classifier and a regression model. So classifier, the same classifier can have infinite pairs of WB. All those pairs of WB end up with this exact same classification results for all the instances.
Is it only for binary classification?
Yeah, for binary classifications. Yeah, that's a very good question. If it is more than 2 classes, if you set up different regions, it's not that won't hold anymore. But for binary classifications, it's a property, right? It's different from like regression, because for regression, if you multiply WB by 10, then your regression function changes a lot. Right? The prediction accuracy, the errors change as well. So for convenience, now that we have so many, as long as we have WB to determine one linear classifier, then no matter how we multiply WB with some positive constant. It doesn't change the classifier. So for convenience, people usually restrict the norm of W to be 1. That means we restrict the W to be a unit vector. And then to perform some analysis. This is also a trick used in support vector machines. And this can be also verified by looking at the classification hyperplane. As you just mentioned, we thought when we multiply WB by like 10, it was stretched, right? But if you look into the hyperplane, so the hyperplane is only determined by this equation. If you multiply WB by both 10, what will happen? The equation doesn't change. As long as the equation does not change, the hyperplane won't change as well. So the interesting observation will be that if we constrain W to be a norm vector, to be a unit vector, then the distance between origin and the hyperplane is simply the intercept, the absolute value of intercept B. So those are all about the interesting properties regarding linear classifiers. Although it is very simple, but it's a foundation for many advanced classification models and techniques. So next we'll discuss how to learn a linear classifier model. How can we determine the weight and the bias or the intercept? So the process is similar to the regression. Right? We collect a set of training instances. So in our case, the training instances would be pairs of the feature vectors and the binary labels. So it could be, suppose we collected like n instances. So each instance is x1, y1, x2, y2, until like xn, yn. So each y1, y2, and yn are either -1 or +1. Then the next step is to come out an objective function. By minimizing the objective function, we estimate the best W and B to determine our classifier. So the question is, how can we come out such objective function? Any idea? The immediate idea is to directly use the SSE for regression, right? So I just ignore the types of y. Anyway, it's just 1 or -1. 1 or -1 are also real values. We just construct the sum of square error, which is a summation over each training examples, and each summation is just the classification function value minus the true label, which is either 1 or -1, and take square. So this is actually the directly inheritance from the linear regression. And we minimize SZ to find out the best weight vector and intercept. So is it good? Is it enough good? It is quite convenient because we can use whatever we use for regression to do this through training. But is it really good? It's really good choice. Think.
Well, it's not any different than the sum of errors like not squared, right?
It's not what?
It's not any different than if you don't, if it's just the sum of the residuals instead of the sum of the squared residuals. I don't know. Why.
Yeah, there's nothing different with linear regression case. I just wonder if I directly use linear regression.
I just mean that inside values are 1, right?
Why?
The like your classifier's output and your minus.
The LXI is some real value.
Right,
It's
so
not,
if they're different, then it's 1.
Mhm.
If it's, or is it?
Yeah, it could be like 1.5, 2, or even 10.
Oh, right.
Yeah, because when we do the classification, yeah, we need to check whether it's positive or negative.
Yeah.
So actually, it is problematic. So you can imagine, we're not trying to enforce our classification function value to be exactly 1 or minus 1. We're just trying to ensure that all positive examples, their classification function value is positive. And all the negative examples, their classification function value is negative. Right? We're not trying to enforce the function value itself to be 1 or minus 1. So this is kind of a bit of a bias. So ideally, we learn a linear classifier which has the minimum mistakes in classification, rather than enforce the classification function value to be close to 1 or minus 1. So there could be some consequence by using this. So here,
a quick question, but is it for two-dimension linear classification problem, it will transfer to three-dimension linear regression problem?
no, it's nothing to do with dimension. It's d-dimensional.
Okay,
D-dimensional.
The second dimension. Okay.
So we can check what's the consequence here. So here, just give a simple example. So suppose I have a few positive examples like this. So here's positive examples. And here I have negative examples. So now I want to learn a linear classifier. So if I simply I draw a line, which is hyperplane, in a two-dimensional space to separate those lines, I can draw many lines. Here is good because I separate positive examples from negative examples, well separate. And I can do this, I can do this. I have many choices. And later we'll explain which choices have the best generation performance. But right now, obviously, I can pick up any line which separate those two set of points. But right now, if I want to find a line which minimizes SSE, guess what do we have? Yeah, because SSE aims to minimize the difference between the label value and function value. So to get this SSE as small as possible, it's very likely to end up with a line like this. Like this. Why? Because you need to minimize the distance between each label. So here's the label, right? And the classification function value. So of course, if I make the line cross this direction, the difference is smaller, right? And for those lines, the difference is smaller. And for those lines, the difference is smaller. If you just like rotate the line like in this way, you can imagine the distance becomes much larger. But if I end up with this line, obviously you can see this is a very bad line. It's a very bad classifier, right? Because at least for this set of examples and this set of examples, they're wrong. Their classification results are wrong. So directly using SSE of linear regression is problematic. So ideally, we want to construct an objective function which, ideally, we want to minimize the number of misclassifications. So if we want to write down our objective function to express this meanings, it should be like this. So we denote this function as a cost function, which is also the summation from 1 to n that corresponds to each instance. And then each segment is 1 minus a indicator function that the sign of the label is equal to the sign of the classification function value. So here, I is the indicator function, meaning that I say x is 1 only if x is true. So if the sign of yi, the labels of ith instance, is the same as the sign of the classification function value, then this is true, right? This is true. Then the indicator function is 1. So 1 minus 1 is 0. That means you are correctly classify this example. You don't have to pay the extra cost. The cost is 0. Otherwise, if you misclassify the example, that means the sign of the true label is different of the sign of your classification function value, then this indicator function is 0. The 1 minus 0 is 1. That means you count 1 mistakes. So this is our ideal objective function to train linear classifier, and called cost function. And we can call it oracle cost function because this is very hard to minimize. Why? This is a discrete function. How can you compute the gradient for an indicator function? It's hard. So this cost function is actually conceptual. So of course you can enumerate, right? You can use some combinatorial search method to minimize this cost function. It's very, very expensive. So in practice, people don't use this oracle cost as the objective function. Rather, we usually come out some proxy for this oracle cost. We call this a proxy function as loss function. So there are many proxy functions or loss functions. Different type of loss functions correspond to different different linear classifiers. So usually the loss function is defined as this form. So loss function is usually still defined as a summation. Summation over n instances, and for each instances, we compute a loss, a small loss. Let me use G, because L represents the classification function. And this loss over one sample is a function of the product between the true label and the classification function value. This is common strategy. Of course, we can choose different G. But usually the input of G is the product between the true label and the classification function value of your model. So what's the benefit of using product? What's the benefit of using product? Actually, the value of this product indicates whether you do the misclassification or not. Why? Because if you do the correct classification, this product is always positive or non-negative, right? If it is correct. If you do the correct classification, you can verify this, right? If yi is just one positive examples, and to make this positive, the Lxi, it must also be positive, so the product is positive. If yi is negative, to make the product non-negative, then Lxi must be negative as well. Right? So when this product is non-negative, it is a sign that your classification on this example is correct. Otherwise, the classification is wrong. For example, if y is 1 but LXI is negative, then the product is negative, right? And if y is negative and LXI is positive, the product is negative as well. So people usually use this product as an indicator of your misclassification. So now let me introduce a few very commonly used loss. The first one is called hinge loss. So what is hinge loss? Hinge loss defined as follows. So here Z indicates this product. It's just the max between 0 and 1 minus Z. This is called hinge loss. And we can check the curve of this hinge loss. So we can draw a curve. So the x-axis is Z and the y-axis indicates the function value. So we can imagine that when 1 minus Z is positive, then this maximum would be 1 minus Z. So when 1 minus Z is positive,
Z is negative.
yeah, Z is less than 1, right? Less than or equal to 1. So that means we can put a mark, the 1 here. So when Z is less than 1, then this function becomes a linear function, right? It's 1 minus Z. So it becomes like this. But when Z is bigger than 1, 1 minus Z is negative, right? Maximum of 0 and 1 minus Z will be 0. So after Z becomes bigger than 1, then the remaining part of this function is just like this. So this is a curve of loss function. Very famous hinge loss, very famous loss.
The name because it looks like a hinge.
Yes, exactly. So what's the relationship between hinge loss and our oracle cost function? We can imagine. We can try to look into it, right? So for our oracle cost function, given each instance, the loss would be what? If we correctly classify the instance, the loss would be 0, right? So what kind of expression can help us to check whether we correctly classify the instance? We just use the product here. This product is positive, then we correctly classify the instance. So here, because the input is replaced with Z, so that means when Z is positive, the cost function is 0. Otherwise, when Z is negative, that means this product is negative, then we misclassify. For example, then the cost function is 1. So we can try to draw the figure for this function here, right? And see what do we get, right? So when Z is bigger than 0, the cost function is 0, right? So here is 0. So that means one part of the oracle cost function is here. However, when Z is smaller than 0, meaning we misclassify the example, then the cost function is 1. Right? So here is 1. So here is our oracle cost function. So now we can say actually the hinge loss is a strict upper bound of the oracle cost. So actually this is some conclusion. So hinge loss perform as an upper bound of the true loss or the oracle loss. It has a very, very nice properties. Usually, if you want to construct a proxy for some oracle cost function, you need to seek for some upper bound to obtain some meaningful properties. And another nice property of hinge loss is that it is convex. Although this function is not everywhere differentiable as well, but it's much easier than the oracle cost function. And this loss, hinge loss, is a loss that is used in support vector machines. Any question? But as we just mentioned, right, even hinge loss, because there's a maximum operation here, it does not guarantee to have a gradient everywhere. It's not smooth at this point, right, at this joint point. So to increase the smoothness, people also proposed smoothed hinge loss and the square hinge loss. So here is the smoothed hinge loss. So which is defined as here. So again, we have 0 when z is bigger than 1. Then this part is the same as hinge loss. But when z between 0 and 1, we have 1 minus z squared over 2. So in this part, when z between 0 and 1, we're not using a line segment. Instead, we use a square function. So it becomes something like this. And then if z is smaller than 0, it becomes another line, 1 over 2 minus z. So if you combine the 3 parts together, the curve for smoothing the hinge loss will be like this. So it's guaranteed to be differentiable everywhere. So you can directly compute the gradient over the SC, over the loss function. But the nice property that hinge loss is the upper bound of the oracle cost is broken. So it's no longer a upper bound of the oracle cost function. And another variant of hinge loss is called square hinge loss, which is also to smooth the hinge loss as well. But in addition to this hinge loss family, another very commonly used loss is called logistic loss. So if you use logistic loss as an objective to train a linear classifier, it's called logistic regression. Logistic regression is very widely used in many classification problems. So what is logistic loss? The logistic loss is defined as ln 1 plus exponential of 1 minus z. So this is a bit different from the concept in hinge loss or other ones. First, it is not a linear function. It's not a linear function at all. And to show the figure, so this is a typical figure of the logistic function. But it has a strong connection with a loss called rectified linear. It's called ReLU. If any of you have like taken some deep learning class or try to play deep neural nets, ReLU is very commonly used to construct the activity functions. It's very popular. And logistic loss can be considered as an upper bound of the ReLU function. And the ReLU function can be treated as just move the hinge loss, and toward the origin, and to make the joint coincide with the origin. That's the ReLU. And logistic is upper bound. So given those different choices of loss, we can construct objective function. Right? So generally now our objective function for learning a linear classifier becomes this is not SZ anymore. I cannot say it's SZ. It's just loss, which is the summation over n instances. For each instance, we compute the loss of the product yi times our classification function value. Right? So because these are functions of b and w, because Lxi couple b and w here, right? So we minimize this loss, we can obtain the best w and b. But in our real applications of classification models, simply minimizing the loss is not enough. It will cause the so-called problem overfitting. So this is a general framework. So in addition to minimizing loss, we also add one extra term. This term is usually called regularization term. This regularization term is usually applied to the weight vector. So what kind of regularization term do we often use? One most commonly used regularization term is simply the square norm of W. And what's the benefit if I want to jointly minimize this loss plus some plus a square norm term of the weight vector? This actually connects to computational learning theory. It turns out that if you choose the loss to be a hinge loss and you choose this square norm of the regularizer, you end up with learning with maximum margin principles. And maximum margin principles can give you the tightest generalization error bound. So if you're going to take my machine learning class in next semester, we'll discuss in more detail about this. So it's not an arbitrary regularizer, some arbitrary regularizer you want to add them. There are some theoretical justifications here. And the second commonly used regularizer is actually called L1 norm, the absolute value of W. But someone may ask, what does it mean? Take an absolute value over the vector of weights. So usually it is represented as a summation of all the absolute values of the weight. So suppose we have D features, right? So this is summation of absolute value of W1, absolute value of W2, and the absolute value of WD. And the benefit of adding this L1 regularizer is to encourage sparsity over the weight vectors. That means that if you jointly minimize the loss plus this L1 regularizer, many features weights will be shrunk to 0 at the minimum. So this is kind of an amazing property. And as to why it will be shrunk to 0, it is beyond our class. And if in the future, if you take some machine learning class, especially talking about sparse learning, it will tell you why you have this like pretty ordinary regularizer. It ends up many 0 estimations. But in general, this is a framework. We add a loss. In addition to loss, we add a regularization term. But we need to choose a regularization stress, eta here. Right? The larger the eta, the stronger the regularization term. Otherwise, the weaker the regularization term. Right? Then how can we determine the eta? An idea? First, it cannot be jointly optimized. If you want to jointly optimize, the eta will be like either minus infinity or positive infinity because it's a linear function of eta. So eta can only be manually chosen. But how can we manually choose the most appropriate eta? And if you have some impression to what we have discussed before. Actually, we have you're required to make some practice. It's called cross-validation. So what can we choose eta? We just pick up eta, which leads to the best generalization performance, right? So how can we verify the generalization performance? Of course, we cannot evaluate infinite number of future examples. Then we use cross-validation. We just split data into the training and test, and then we try a range of eta, right? See, 0, 0.1, 0.1, 1, 1.5, and continue, right? For each specific eta, we just use the eta and then train our model and test it on test data set and do it multiple times to get cross-validation accuracy, right? To indicate its generalization performance. Then we'll have an evaluation for one eta. Then we try another eta and use the same procedure to get the cross-validation accuracy again. And then when we have tested all the etas and get all their cross-validation accuracies, we just pick one with the highest accuracy. That's the normal way to choose them. That's regularization strength eta. Any questions? Okay, we should stop here and see you next Monday. Have a nice Thanksgiving.